Okay, so next we are going to give you more ideas about the difference or the relationship between the thermodynamics and kinetics. So thermodynamics actually equilibrium always talk about the equilibrium conditions only. So thermodynamics can help us to define the specific states, right? So in this schematic, these figures, then you can find that actually there are 6 states defined by thermodynamics, and definitely all are equilibrium conditions. And F means the state can be the state function, for example, like the energy state function. And we also can put some parameters to describe the state we're talking about. So as you know, the state of a material system, we can use the thermodynamics to predict the state function or state of a material system under the thermodynamic equilibrium. And the thermodynamic equilibrium, the characteristic of thermodynamic equilibrium is the state function does not change with time. So we call it equilibrium conditions. So first of all, we know the state. Then next, we want to know if we have state 1, then want to move to state 6. So probably you will the path you choose will be from state 1 to state 3, then move to state 6. This is the path 1. Or you will say, how about I can choose the other path is from 1 to 4, then to 6. So kinetics process actually is depending on which path you choose and the corresponding rate involved in. So now you know, in order to deal with or estimate the rate of kinetics process, first of all, you need to use the thermodynamics to help you to define the states of your material systems and find out the start and ending point, or start and ending state in your material system. Then you need to decide which path you are going to choose is 1, 3 to 6 or 1, 4 to 6. And next you are going to calculate or estimate the rate involved or corresponding to the path you choose. So I'm going to give you an example which you're familiar with will be the ideal gas, right? What's the ideal gas is the P times V equals nRT. So as you know, if you try to adjust of pressure or the volume, that will lead to the change in mass and temperature. As long as you have the change of mass or temperature, that means there's definitely a mass flux and also the heat flux passing through your material system, right? So for example, like people usually will use the gas cylinder for keyboard cleaning, right? You want to cleaning the keyboard on your computers, so you use a gas cylinder, right? The temperature will drop after the gas stream release out of the cylinder. That's it. Everyone have this experience, right? Okay, so when you release the gas stream from the gas cylinder, the P is decreased, right? And T accompany the temperature drop in the same time. So during this process, actually, is from state 1, one state of state 1 passing through state 6, something like that. So no matter the start and ending point, which start and ending point you choose, but the most important part involved here is as long as you change the pressure and volume, and that will lead the mass and temperature change. Then you will find out the mass transport and heat flow happen in your system. So that is a typical kinetics process. Okay, so I'm going to give you a summary of the thermodynamics. Actually, thermodynamics provide a baseline for describing the state of a material system under equilibrium state. So they help you to define the equilibrium, the state of your material system. And we can use various types of energy state function to define the state of your material system under different parameters or constraints, including pressure, temperature, composition, defect, or charge state, and so on. And when a system reaches thermodynamic equilibrium, there are two characteristics. The first one is no spatial variation in chemical potential. What's the no spatial variation means? Spatial actually is what? And in chemical potential, that tell you the chemical potential everywhere are the same, right? Are the same everywhere. So if you draw the chemical potential as a function of location, then you can get the chemical potential are the same. So that will lead no mass transport because no driving force, no net mass transport. But I will want to highlight the net means the atoms still jumping to right to the left, but there's no net mass transport. That means at the specific location when you calculate or measure the concentration, the net the concentration, the atomic concentration does not change with time. That means there's no net mass transport. Some atoms jump to the right, but there's definitely some atoms jump to the left. The total, after you have summation of them, there's no net mass transport because there's no driving force exists in this system. And the second part will be the total free energy is a minimum. So when you reach equilibrium, the total free energy system of the system is minimized. So if you want to describe more details in this sentence, then you can say any movement will raise the free energy of the system. Under this situation, then you will say, oh, now the system now is the total energy of the system is minimized. Okay. So next, I'm going to give you examples because previous one we just put more efforts on the difference between the thermodynamics and kinetics. Then here I'm going to take a chemical reaction or phase transformation process as an example to tell you how important why the thermodynamics and kinetics is so important in chemical reaction and also the phase transformation process. So now we have a chemical equation. Reactant A will react with B, then probably they will generate C and D. Probably means we don't know whether the reaction direction is to the right-handed side. In order to understand the reaction directions in these chemical equations, so what we can do here is we can draw the free energy, Gibbs free energy versus the reaction coordinate. And we can calculate the total Gibbs free energy of A and B. Then we get this red curve here. And also you can, so we label 1, state 1. And you also can calculate the total Gibbs free energy for C and D. You sum them up so you can get the total free energy is 3. So based on here, we know what the total free energy at stage 3 means the C and D is smaller than that on stage 1 means A and B, right? So let's for this one we know that the delta G, this G minus this small g minus larger g, then you know the total gives energy is negative, smaller than 0. That tell you this reaction definitely will happen. So we call it thermodynamically favorable because delta G is smaller than 0. But thermodynamics only tell you, yes, this chemical equation will go to the right-handed side. But the one thing, very important part they didn't tell you is how fast or how slow the rate of these chemical equations. They didn't tell you. So that part will be involved. Which will dominate the rate will be the energy barrier at the stage 2 here part. This is energy barrier, and some people call it as activation energy. So as long as the reactants have sufficient energy to overcome this energy barrier, then we can have a product. So in this case, we know if the energy barrier or activation energy is smaller, then that will speed up this chemical equation. So we call it as a kinetically favorable in this case. Then next, now you have some pictures, right? Pictures and idea about the kinetics, right? Okay, so I will put more, we can give you more idea to talk about the kinetics here. So thermodynamics equilibrium conditions, but kinetics, what about kinetics? Thermodynamics, the state function, the functions does not change with time, but kinetics actually definitely the state function change with time. So the rate of state function evolution always can observed in kinetics process. So the state function change with time. So the state function can be the free energy and also the entropy part. And as you know, this energy also will involve the changes in shape, size, composition, and crystal structure of materials. So state function changes. So the rate of state function evolution is very important in kinetics. And kinetics, as you know, is there's a flux passing through, right? So this process actually definitely is from deviated of equilibrium state toward to equilibrium state. Otherwise, if both side or both state are equilibrium state, it's very difficult to have a flow process, right? Flow process means that there's definitely the flux passing through. If the material system already in the equilibrium state, that definitely need a force to push the system deviated or deviation from the equilibrium state. Then when you release the or stop the driving force, then that will back to equilibrium state, and the corresponding path and rate is what we are care about in kinetics. But in this case, some people probably will concern about, in this case, this kinetics process, it turns out is a moving or flow process, right? So how can we use the energy state defined by thermodynamics into kinetics? Because thermodynamics always talk about equilibrium state. How can we use the energy state function defined by equilibrium state to use that into a kinetics process? It's not reasonable, right? So in order to help us to deal with that, so we will make a very important assumption here. Yes, kinetics is state function changes with time. The rate, we care about the rate of state function evolution. But in order to allow us to use the energy state function we derive in thermodynamics, so we will make a very important assumption here. We will assume the local thermodynamic equilibrium. So in this case, probably I can give you some examples to describe here. So let's move to probably this one. Okay. In the beginning, if we have the same metal bar, we just put the metal bar at room temperature, and if you try to draw the temperature as a function of like location, what you get here, definitely you will find this, right? This T state function. So the state function here, T temperature, does not change with time. But if we put a hot reservoir at the left-handed side to provide some heat to this metal bar, and we put a low reservoir on the right-handed side to receive some heat released from this metal bar. As long as the Q in equals to Q out, then we can find the temperature the state function temperature distribution was like this, right? And as long as the Q in equals to Q out, so this temperature profile does not change with time as well, right? So under this case, if you take here, so you know at this location, the temperature does not change with time. But so if you zoom in this region, what you will get? Yes, you can consider that is a local thermodynamic equilibrium, right? If you zoom in, although there's definitely when in the macro scale, there exists a temperature difference along this metal bar. But what we want to do here is we zoom in this small region, and under this situation, we can consider this is a local thermodynamic equilibrium conditions. Okay, so let's back to the because we assume the local thermodynamic equilibrium in kinetics process, we can in this case, we can use the energy state function we derive from previous slides we can use that equations in kinetics process. And if you want to put more specific, if you want to know which parameters or the rate of state function changes. So next question would be, what parameter will affect the rate of state function changes in kinetics process? The first one come out from your mind, but probably will be kinetics, right? It's a flow process, right? So first of all, you will think probably it's a driving force. So what's the magnitude, and for what's the time period of the driving force applied on the systems? And the second part will be the system inertia or the mobility of the system. So in inertia or mobility of a system means when I apply the unit of driving force, what's the velocity of this material, so what's the rate of this material system. So let's take this as an example here. If we have a trunk and a sports car, then we use the same engine with the same horsepower, we use this for the trunk and sports car. So which one will run faster? With the same engine with same horsepower. So I guess probably you will say the sports car, right? In this case, the engine actually serves as a driving force in this situation, and the trunk actually is heavy than the sports car. So inertia of the system for the sports car is smaller, besides it's lighter, right? So due to this reason, so we can say, oh, the sports car probably will run faster. So in this case, when you want to determine how fast this kinetic process is, you need to consider two parameters. The first one is driving force, and the second one will be the inertia or the mobility of the system. So I want to write something here. So let's take the other example here. I apply as the example we just mentioned in previous last slide, if I apply temperature gradient across on the two ends of metal bar, and I apply temperature gradients, right? Okay, and that will lead what? Will lead the heat flux passing through that metal bar, right? Okay, so in this case, driving force will be the temperature gradient, right? But in this case, what's the inertia of the system? It's very difficult to you to think about that, so probably I can expand the answers again. If I have two metal bar and I apply the two different materials of metal bar, I apply the same temperature gradient at the two ends of this metal bar, do you think the heat flux will come out the same? Or the temperature grade distribution? The answer will be no, right? So that means there's definitely a material property serving the inertia of a system definitely related to a material property, that will be the thermoconductivity kappa. So here in this case, driving force will be a temperature gradient, and the inertia of the system will be the thermoconductivity. So the other is that if I apply the electrical potential across at the two ends of the metal bar the same, then that will generate the current, right? Current. The same thing. So the electrical potential serving a driving force, and in that case, what's the system inertia of the system? So the same idea, right? If I apply the same electrical field or electrical potential on the two ends of two different materials, would that be the same current density? No, right? So you need to additional consider the inertia of the system. So the property here would be electrical conductivity. Ding, ding. Right? Okay, so let's move forward. So now I hope you already have some idea about this driving. In order to describe the this kinetic process is faster or slow, happens faster or fast or slow, you need to consider two parameters: driving force and inertia of the system. So now I'm going to give you 3 different examples, and hope you can quickly find out the driving force or inertia of the system. So the first one is the melting process. So I have ice here. Then the ice, after a while, the ice will melt into water. So I have the ice, so when the ice have absorbed the sufficient energy, then the structure of the ice will randomize and becomes to liquid, right? So in this case, if you use the temperature as a state function, then is this a kinetic process? Then probably you will have a little bit concern, right? Because during the melting process, the temperature does not change with time. If you use the temperature as a state function, that does not change with time. So probably you will say, oh, is a melting process a kinetic process? But that state function does not change with time. So I would say you need to consider other state function. In this case, entropy, if you use entropy as state function, entropy changes. Entropy increase in this case. Okay? So melting process actually also a kinetic process, and that will also involve the rate, because how fast or how much heat how much heat be absorbed by the ice, that will determine the melting rate, right? Okay. And the second example we call the creep. Creep means actually if you have a metal bar and subjected to a uniform stress, and after a while, after several years, so after for a long time, then we can observe this kind of metal bar get longer and longer and have some strength. Then that is we call the creep. And the reason behind or mechanism behind actually is this metal bar is under a stress field, and then this stress field will drive the mass transport or diffusion, and which will lead the metal bar get longer and longer. And if you try to find out the driving force, will be the stress field gradient, and that will result the strength, right? Because that will get longer and longer. And what's the inertia of the system here? It turns out the stress field drive the mass transport. So every material has the mass transport velocity, which material related to the mass transport velocity, I would say is the diffusivity of the system. And the results, the purpose here definitely is minimize the system free energy, okay? And some people will call about as I remember, you learn that that creep is easily observed in high temperature, right? And which is match what you learn here, right? Because at high temperature, the diffusivity is higher, right? So the result turns out consistent. Okay, so the third example here will be the grain growth. What's the grain growth? That means, first of all, definitely what we have is a polycrystalline materials, and we observe that the size of grain increase and the total numbers of grain decrease. That means some grain growth get bigger and bigger, and some grain shrink and disappear. And the purpose here is what? Also, not the purpose. The reason for this actually is the energy of the grain and the energy of the grain boundary are different. The energy of grain boundary usually is higher than that in the grain. So when we have materials, if there are many or higher volume ratio of volume of a grain boundary, that means the total energy is higher. So system is tend to decrease its total free energy, right? So the volume or the ratio of the grain boundary should decrease over time. So the result turn out would be what? The grain will get larger and larger. So that is the that's only method to decrease the volume over grand boundary, right? So the purpose also is minimize the system free energy. And also the inertia of the system here is also the diffusion, so it's also the diffusivity. Okay, so today we just ended here.